All right, class, we've been down for a while, so we're a little behind. I wanted to give extra time for the midterm, so we're behind in Chapter 11, but we're going to cut out some stuff just because I think this online environment is hard for some people compared to a face-to-face, and I just wanted to give a little bit more time for people to prepare for the midterm, and then I had a not power hours, but an internet down all day yesterday, so I'm back to it now. So we're going to start with Chapter 11, which is some probability and statistics type things. We're going to kind of not going to hit everything in here, but we're going to hit most of it, and we'll be fine because a lot of these chapters are semi-optional anyway in the outcomes and objectives, so we'll be all right. We're going to first talk about in Chapter 11, the fundamental counting principles with two groups of items. So the idea is if I go to a restaurant, let's say, this is kind of a common motivation for these problems. So if I go to a restaurant and I've got two appetizers and another one, and then I've got three meals, main meals I could have. So main dish number one, main dish number two, and then main dish number three. So I have two possible appetizers. The question is, how many different full meals could I have? Well, if I were to diagram this, how many different meals could I have with an appetizer and a main meal? Well, I could draw a little tree diagram here. I'll draw it below this line. I'll call this appetizer 1 and appetizer 2. I can pick between either one of those two. And then after having appetizer 1, I could either have main meal 1, main meal 2, or main meal 3. And if after appetizer 2, I could choose main meal 1, main meal 2, or main meal 3. So how many total choices is that? Well, this is choice 1, which would be appetizer 1 with main meal 1. This is choice 2. This is combination 3. This is choice 4, 5, and 6. So those are all the different kind of combinations of one of the two appetizers and one of the main meals. So there are how many of them? 6. There are 1, 2, 3, 4, 5, 6 of those. Do you see that? Okay. So we have 6 possible combinations there. It isn't a coincidence that since there were 2 appetizers and there were 3 main meals, that the total number of possible appetizer main meal combos is 2 times 3, which is 6. Okay, so if we have some different options with 2 groups of items or 3 groups of items or whatever, the way we find the total number of possible combinations of those, or we pick an appetizer and then we pick a main meal, would be you just multiply the numbers. Okay. Okay, that brings us to something I call the fundamental counting principle, or I don't call it. This is a probability concept. If you can choose one item from a group of m items and a second item from a group of n items, then the total number of 2 item choices is m times n. That's just what I just kind of went through with the example with the meals. And now let's just do a couple examples. This is all there is to this section, so let's just do some examples and get used to this. Okay, so let's do this problem. For a temporary job between semesters, you are painting the parking spaces for a new shopping mall with a letter of the alphabet and a single digit from 1 to 9. The first parking spot is A1 and the last parking is Z9. How many spaces can you paint with distinct labels? Okay, so it's really a pretty simple problem. Your total number of choices is going to be m times n. Well, how many choices do we have for the first? With the letter of the alphabet, we have 26 letters of the alphabet. And then digits from 1 to 9, that's 9 things. 26 times 9 is 180 plus 54, which is 234. Pretty simple problem. Okay, let's try this one now. The local 7-digit telephone number numbers in Inverness, California, have 669 as the first three digits. So that's your 669. How many different telephones are possible in Inverness? So there's 4 left. And for each of those spots, how many choices do we have? I'll write those in. You can have 0 through 9, which is 10 choices. So there's 10 choices for each of those. So the total number is going to be 10 times 10 times 10 times 10. Since there's 4 different choices there in sequence, we have to multiply. Normally, the fundamental counting principle I gave you is only for 2 choices, but you can extend it to 3 choices or 4 choices in a row by just multiplying all of them together. So that's 10 to the 4th. That's 100 times 100. That's 1, 1, 2, 3, 4. That's 10,000 different phone numbers. Okay, that's it for 11.1. That wasn't too bad, was it? Okay, now we're going to move on to 11.2, and we're going to talk about permutations, okay? So permutations is all the different ways that you can order things. So we're going to use the fundamental counting principle first to think about some of these problems, and then we're going to build to what a permutation is. We can use fundamental counting principle to determine the number of ways jokes can be delivered. Okay, let's say there's a comedian delivering jokes. This is coming from your book. This is a great example, so I just copy and pasted it out of there. You can choose any one of the 6 jokes as the first one. Once this joke is delivered, you'll have 5 jokes to choose from for the second joke. Then you'll have 4 jokes left to choose from for the third. Continuous manner to the situation can be shown as followed. So there's 6 choices to begin with. Then after you've done one of those choices, only 5 choices. Then after you've done the other 2, there's only 4 choices. And every time you tell a joke, there's less choices for the next joke. So we use the fundamental counting principle. We multiply the choices as 720, so that means there's 720 different ways to deliver the 6 jokes about books. These are jokes about books. That's part above this I didn't copy down. And so that tells me how many different possible ways there are to tell these jokes in different orders. There's 720 different ways to tell these jokes in different orders. Okay, so this is a way that we think about this using the fundamental counting principle. Okay, so if I do a problem like this, very similar, in how many different ways can a police department arrange 8 suspects in a police lineup if each lineup contains all 8 people? So if I line them up, here's my lineup. There's 8 spots, right? Well, in the first spot, I've got 8 choices of people. After I've put one person in that spot, I only got 7 for the next one. Now I put 2 people in spots. I only have 6 choices of people to put there, and then 5, and then 4, and then 3, and then 2, and then 1. So the answer, to get the number of possible lineups, it's 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, which I put into my calculator. 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And I get, there's 40,320 different possible lineups. Okay, that should make intuitive sense to you. We could make a tree diagram for this to show it, but it would take too long with that many choices. Okay, so that thing we just did, the 8 times 7 times 6 all the way down to 2 and 1. Skipped a few numbers in there. There's a way to abbreviate this product right here, and it's 8 factorial, okay? And I have the definition of a factorial up here. This little exclamation point means factorial in mathematics, okay? So basically, if n is a positive integer, the notation n factorial is the product of all the positive integers from n down to 1. So basically, if I'm doing 8 factorial, it'd be 8, this would be 8 times 8 minus 1, which is 7, times 8 minus 2, which is 6, all the way down till I get to 1, okay? So that means that like 6 factorial is 6 times, 5 times 4 times 3 times 2 times 1, and so on and so forth. On the calculator, you can do factorials, and you should learn to, because you don't want to do all these by hand. If you're doing like 20 factorial, you're going to be typing in a lot of things in your calculator. 20 times 19 times 18. If you hit the math button and then scroll over to the probability tab with your arrow, and if you go to the probability tab, look at number 4. That's your factorial button. So the way you do this in your calculator is you hit 18. If you want, or sorry, my bad. Let's do what we just did. Let's do 8 factorial. What you would do is you'd hit 8 factorial. The way you do it is you'd hit 8, then you hit your math button, then you'd scroll over to the probability menu, and then you'd hit 4. And then you'd hit enter. That's the actual order of your keystrokes. So, and that should give you what we got a minute ago. All right. Okay, now we're going to talk about permutations. In the examples we've just done with the jokes, there's 6 jokes, and we're going to deliver all 6 jokes. Or there's 8 people in a lineup, and we're going to line all 8 of them up. So what happens if there's 8 people in a lineup, but I'm only going to choose 5 of them to line up? So now I have a total group of 8, and I'm only choosing 5 of them to line up. How would I figure out how many possible lineups there are with 5 people choosing from 8 people? That's a permutation. A permutation is when you're choosing a certain amount of options from a larger amount of options, and you're putting them in a particular order. So order matters, okay? So here's an example that builds this theory. You're the coach of a Little League baseball team. There are 13 players on the team. You need to choose a batting order having 9 players. So you're choosing 9 out of the 13 to line up in an order. The order makes a difference because, for instance, if bases are loaded and little Albert is 4th or 5th at bat, his possible home run will drive in 3 additional runs. How many batting orders can you form? So how many different batting orders are there? Possible different batting orders are there if you're choosing 9 people from 13 people to line up? You can choose any 13 players for the first person at bat. Then you will have 12 players from which to choose. Then you'll have 11 to choose, and so on and so forth. So batter 1, I have 13 choices. Then after I picked one, I only have 12 left, then 13. And basically all the spots get filled, and I in the very end, I have 5 choices because I didn't use all of the possible batters. So the total number of batting orders is found by just multiplying all those choices in sequence. Okay? So that's the total number of batting orders right there. One way to look at this formula and to build this formula is if I'm choosing 9 people from 13, this numerator, if I take 13 factorial, which is that numerator, and I divide it by 13 minus 9 factorial because I'm not using everyone, it turns out I get the exact thing I'm looking for. That's going to turn out to be a pattern. So the way to think about this is this is the notation for permutation. Okay? This means choose 9 from 13 to order. So we're choosing 9 things out of a total of 13 things to put in a particular order. Okay? So let's experiment around with this. Okay, so here's the formula for permutation. The number of possible R items are taken from N items. So if you're choosing like 9 items from 13, like an example we just did, you use this formula to find the number of possible orders that we could have. So a corporation has 7 members on its board of directors. In how many different ways can it elect a president, vice president, secretary, and treasurer? So we've got 7 members total. The way we'd write this is NPR. In this case is 7 permuted. And it looks like we're doing 1, 2, 3, 4 rolls. How many different ways are there for us to put those in those rolls? So that'd be 7 permuted 4. So that would be 7 factorial over 7 minus 4 factorial. Okay? So the way you can do that is 7 factorial over 3 factorial. You do it on your calculator. So using the factorial button like we just talked about. So I'm going to do this right now. That'd be 7, hit the math button, scroll over to probability, go down to factorial, number 4, divided by 3 factorial, hit the math button again, so hit the 3, and then the math probability, hang on a minute, and I get 840. 840 different ways. Okay, so this is our general formula. It turns out, guys, that you can actually do this NPR directly on your calculator without even doing the factorials, and that's the fastest way to do this. I'm going to show you how to do that right now. Okay, I'm going to explain it anyway. I can't show the video of it, but so to do like 7p3, like we just did, what you do on your calculator is you hit the 7, so hit 7, and then you're going to hit the keystroke for math, or hit the math button, scroll over to the probability menu with your arrow, and then look at number 2, which is NPR. You should see that. So hit the number 2 on your calculator, and it'll select NPR. So now what you should see up to this point, what you should see written down after you hit all this, is 7 on your calculator. It should look like this, 7 NPR, okay, is what you should see on your calculator. Now just hit the 3 button, and then hit enter. So hit 3. So after this point, now after you hit that 3, what you should see in your calculator is 7NPR3, and then just hit enter. Okay. We did 7NPR4 in the last problem, so that's why we're getting a different answer. This is 7NPR3, 7P3. So that's how you can do this in your calculator using the keystrokes, okay? And by the way, your Easter egg guides is 051206. 051206 for this video. Okay, now let's do some problems. In a production of West Side Story, 8 actors are considered for the male roles of Tony, Riff, and Bernardo. In how many ways can the director cast the male roles? Well, isn't this using NPR? My N, there's 8 actors, and there's 3 roles. So wouldn't this just be 8P3, which on my calculator is 8, then go to the math menu, over to probability, select the NPR, and then that'd be 3. It's 336. There are 336 different ways to cast that out of the 8, to cast 3 people out of 8. Okay, let's try this one now. A camp counselor and 6 campers are to be seated along a picnic bench. In how many ways can this be done if the counselor must be seated in the middle and a camper who has a tendency to engage in food fights must sit to the counselor's immediate left? So this one isn't one where you can do the permutation equation, and here's why. This is one where you just do the fundamental counting principle, because if I just imagine my 6 seats, actually there's 7 because there's a camp counselor and 6 campers. So there's 7 total. It says the camp counselor goes in the middle. So put the camp counselor there. Let me see here. So this is the counselor. Okay. And then there's a bad student who has to sit right to the left. So the bad student goes here. All right. So now, for this spot, how many are left? How many choices are left? We've already seated 2 people. So now we've got 5 choices here. Once we seat that person, we only have 4 left for that one. Once we seat this person, we only have 3 left. The other 2, we only have 3, then 2, then 1. So this would be 5 times 4 times 3 times 2 times 1, which is 20 times 3 is 60 times 2 is 120. 120 different ways once we seat these 2 people right there. Those people are stuck there. And the other ones, those are the choices we have. Now, in all the examples that we've done of choosing an order, we've never allowed there to be duplicate items. Like, let's say we have 2 apples, an orange, and a pear, and we're going to find all the different ways to order those to get different orders with those things, but we have two repeated apples. So it kind of changes everything, doesn't it? Because we could do apple, apple, orange, pear, and we could do apple, apple, pear, orange, and we didn't even move the apples, or we maybe switched the apples, but it's still apple, apple, pear, orange. So what if we have duplicate items that are repeated? How do we handle that? Well, we have a different permutation formula when we have some duplicate items in our list of things we're choosing from, okay? In our list of things we're choosing from. None of the examples we've had were there any duplicate items. There were 6 different actors. There were 13 different ball players. They're all unique individuals. So the number permutation of the n items where p items are identical, q items are identical, r items are identical. So for example, let's say I have 2 oranges, 3 apples, 4 pears. What's the number of possible ways I could order all those things? All right, so let's take an example, and I think this will become a little bit more clear. Okay, so for example, how many distinct permutations can be formed using the letters of the word Tallahassee? Well, I want you to notice, first of all, how many different letters are we going to be using here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so let's start with that. So there are 11 is my n. Okay, so we're going to use this formula, but 11 is going to be my n. Now, let's look at the ones that are duplicates, where p items are identical, q items are. So look at all the repeated items. Okay, well, looks like there's L is repeated. So L is repeated twice. Okay. Looks like S is repeated twice. Looks like E is repeated twice. And looks like A is repeated 3 times. So the numbers where P items are identical, Q items are identical. So basically, these are all my repeated or identical or repeated items. So, and nothing else is repeated, right? There's only one T. Do I have the L's? I have the S's, just double checking I got them all. The E's and the A's, yep. So this whole thing would be n factorial over, looks like there's 4 repeated items, p factorial, q factorial, r factorial, and s factorial, because I have 4 different repeated items. So this would be 11 factorial over 2 factorial, 2 factorial, 2 factorial, and 3 factorial. Okay, and I get those numbers from this, 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 and that. So that's how I would do this, because we have some repeated letters. And so let's plug that into the calculator. And the way you plug that in your calculator is I just do the bottom first. So that'd be 2, well, you can plug it in. You don't really need it for 2 factorial, but you could plug it in. 2 factorial times 2, takes a minute to do these factorials, factorial times 2, scrolling over, factorial times 3 factorial. My bottom is 48, and my top is 11 factorial. So I'm just going to do 11 factorial right now. 11, then use the math button to get your factorial on. And I'm going to divide that by 48. And I get 8,31600. That's all the different ways. So that's how we do duplicate items. So that should get you done for the homework today. Should be all set.